And this is what we call fractography, and this is what we regularly do when we look at these materials that fail. So don't throw your failures away, but look at them and try to understand them, and then hopefully you can prevent that process occurring next time. Another former student, Jim Ironside, again, this is a failure of an insuram system. And he saw this chipping process or cracking problem, and again, he was able to extract that crown afterwards and look at it. Sorry, I must have thrown that other part away. But he had to blame himself as a prosthodontist. He had made the coping material too thin, and there was a gap underneath it, so this was the origin of why this system failed. Now, when you're going to make these materials, one of the issues that often conservative processes, you would like a very tapered margins at that edge to be able to minimize the amount of tooth structure removed. But the problem is that often then leads to a very sharp ridge-like structure, and that sharp ridge makes it very easy for cracks to initiate from this area. You notice this is 200 microns, so you have a very, very sharp edge. And it's, even though you have a strong material here, when you have such a thin section like this, it is very easy to nucleate a crack here. Once the crack is nucleated, then it will easily grow in that system over time. Every time you bite, you get a stress concentration at that system, and that crack will grow over time. Now, if we look at some of the survival processes in these systems. Again, this is relatively older work looking at some of the insuram materials that are available, and again, after 5 years, 92%. Some people have gone up to 11 years, and they've got 65%. So there are failures occurring, but the process here is they're not distinguishing whether the failure is due to caries or due to fracture of that system. Now I want to switch now to this group of materials. This is the zirconia, because this is the higher strength, higher toughness material. What is the failure probability of those? Now the data is very limited, it's only relatively 3 to 4 years. This is the Premolar system, and relatively, essentially, none of them have failed. But we're getting this chipping problem. 15 to 20% of them are chipping, and severe chipping. So what do I mean by chipping? Excuse me, I'll diverge one moment at this point. This is some study with a former graduate from Cairo University, Ayman, and Tanapon. And this was triggered by some work that we were interested in terms of a failure of premolar and molar materials. And this slide happens to come from Geneva again, where Professor Shearer, and she gave me an example of this, where you can see this crown is completely cracked, and the crack is initiated from the base of the fissure of that system and the occlusal process. And this is the fracture surface that is there. Now what we were interested in doing was looking at posts. We had some zirconia posts, and we had these different materials that were built up into them. We had zirconia coping. We're interested in whether it was the thickness of the zirconia coping was important, or we're interested in whether the angulation of that post, whether it was normal, 15 or 30 degrees inclined, was important. And these guys, well, I was not initially involved in this story, and I don't like these tests. It's a classic crunch the crown test where you just load it up until it fractures. I don't like this test, but I did get involved. And what they found was that they got extreme scatter. Now, apologies, you can't see the range of lows, but the Weibull values between 1 and 2, so the scatter in the results range from 100 or something like 500 newtons to 2,000 newtons. And the scatter was terrible for all of this data. And there was no clear trend of angulation of the post, no clear trend of thickness of the zirconia. So we decided to look at this in another way. We essentially looked at these crowns and said, because they were handmade and there were slight differences between them, we looked at them and tried to look at them in terms of what is the effect of occlusal angle that is associated with this. And we initially did a very simple process. We just measured the width of to the cusp, we measured the height, we measured the depth to the fissure, and on the basis of that, we then looked at all of that data that was generated by these people, and we plotted the failure load against the cusp angle, included cusp angle. And all of a sudden, data that was tremendously scattered began to rationalize more critically. Secondly, we started to look more critically at some of these samples, these ones that are in coloured discs, these coloured circles. Initially, when we made the calculations, it was the cusp angle, it was the value that we had in the circles. And then what we did is that we then re-looked at some of those materials, and you can see here, this is how we calculated the angle, but when we looked at more detail, then we could see that there was, in fact, this was a totally inappropriate calculation of the angle because the angulation was very different. So these were the 4 different materials we looked at, and on the basis of that, when we recalculated, then we moved the samples in the direction of the arrow. So one of them moved very much to the left, to the right I mean, and the other 3 moved very much back to the left. So we got a very neat relationship between the failure load and the cusp angle for all of these materials. And again, why was this? You can see the fracture initiated from the base of the cusp. There was a very thick layer of the porcelain material on top of that, and we were able to get quite consistent outcomes. When we looked on the SEM, we could see that the crack is initiated but in this cuspal area, in the saddle point in that, and we could follow that crack growing down that system. So how to make progress? How do we actually interpret that? Now, my background is in materials and physics and mechanics, and so one of the ways that we do fracture tests in metals and many other systems is what we call a compact tension test. And that's this test here. And then I felt that, well, this is not too remote from the crown system that we use. So here is the crown, and here is how it was loaded. So we could then reinterpret that in terms of this test here. We have a ball or a cylinder that's loading. We could determine from the radius and the angle of the occlusal system where the system was loaded. So we have the crack dimensions. We could know from the force and this resolution of forces what the horizontal component of that stress was. And so we could then use this simple model to reinterpret this process. And so this now enabled us to determine a relationship between the critical load, the fracture toughness of the material, the angle of the system, and the radius of the system that we loaded it with. And this is the fit that we get to that process. And when we went through the data, this is what we measured, what we calculated for this system was 1.8, and what was measured was 1.66. So we get a very comfortable agreement between the systems. What is the consequence of this?